Okay, it's not morning, it's afternoon, so good afternoon or good evening from New York City. It was freezing up to this, it got mild out, so I'm about to head off on the motorcycle way up to Dobbs Ferry for a glass of Radburger. Now, I'm continuing with quantum field theory towards renormalization in its simplest possible case, right? You can add more loops to it, you can make complications to the calculations, you can just make many bigger things. It doesn't change the general structure. So I'm trying to keep it in a way that a student can learn what the structure is. Now, I'm out by a factor of 2 in here somewhere towards the end, but you know, some astute watcher can find out about it. I'll tell you when it comes up. So what I'm going to do is I'm going to renormalize a lambda phi to the fourth to first order in lambda. So towards renormalization, and I'm going to use my notes because it's simply too much for this case. Not too much in terms of the structure, but too much in terms of little numbers like i's and, you know, lambdas. So that's what I'm going to do. I'll take a look at it. I won't use everything, but I'll sometimes refer to them. So the general idea is this. So we're looking at the generating function, and you actually don't need to know this. That's for people who are in detail with this. And I left out a lot of the detail that you get in quantum field theory books. I'm doing quantum field theory entirely in terms of Feynman diagrams and their Feynman rules and their diagrams. And then I will calculate results. So you only need to be able to calculate cross sections, let's say, of results. That's what physics is all about, getting answers. Now, I think there's a minus sign there. The general idea is we have a generating function which can be expressed this way too, and it's calculated in terms of the path integral from which you can derive the Green's functions. I'm only doing a 2-point Green's function. Now, 2-point Green's function, you can have 4 points, 6 points, and so on and so forth. That's all I'm doing it. And we're looking at the, oh yeah, everything is in Euclidean space. That is topic for a whole full half-hour lecture. Now, so the Lagrangian that we're sticking to, I guess I have a no sign there. No, it's like this. So the action now we both mu's are lowercase because it's Euclidean space. And we have been working with scalar fields, lambda phi to the fourth, not lambda cubed. I did some lambda cubed example. Now I'm going to add a source term which will go away in a minute. That's just for getting these things. 2-point Green's functions. Because we're only going to use the Feynman rules and then do calculations. We're going to calculate out this plus this, right? We're not going to higher order than that for lambda phi to the fourth. All right, so what else can I say? So the Feynman space, the Feynman rules for this case is the propagator 1 over p squared plus m squared. The vertex momentum flowing in gives momentum flowing out. Basically, it's Kirchhoff's rule. What else do I have? Well, integral over loop momenta. There's a factor of 2 pi to the 4th in it. What else? And to get from one space to another, we have to find, of course, the Fourier transform. P1, P2. As usual, the Fourier transform takes the normal situation of Fourier transform to momenta space from position space. And we're only dealing with 2-point Green's functions like this. Now I calculated, I got to this point before, so you have to look at the previous lectures to see where this guy came from, right? And we say this is the diagram that looks like this. Q is the loop momentum, and P is, okay. You have to go back to the previous lectures to see how I got up to this point. So far we've done all of this, and I'm just continuing on, just showing you where we got to. And here's Lagrangian. I'm going to get rid of that now. That's kind of a recap. Quantum field theories 2 and 2A and 2B, I can't remember. So let's continue. So we want to evaluate this then, basically. We want to get this guy here. We want to evaluate this. We're going to use dimensional regularization. Dimensional regularization due to 't Hooft and Veltman. We're only employing one of the several formulae. There are different formulae obtained by successive derivations. To get to dimensional regularization, we have to adjust our Lagrangian. Now we adjust the dimensionality of the space. We also adjust the coupling constant. And we don't keep our sources, all right? Now, okay. we're going to let epsilon equal 2 minus omega. So d to the power of 2 omega so omega is 2 minus epsilon. So that the differential operator, when we take the limit of epsilon goes to 0, we get back to d to the 4. That's what's going on up here, and the same is true for this. That becomes a 2 pi to the 4th. Now we also introduce a new mass scale. All we've done here is we have redefined lambda to go to lambda dash, and this is the form of the lambda dash. We need a new mass scale. So what can I say? Oh yeah. So 2 omega is 4 minus 2 epsilon every time we see this crop up. Just have to keep that in mind all the time. And this is due to 't and Veltman. Is there anything else I can add to this? Okay, now I'll just write down the dimensional regularization formula that we are going to apply from 't and Veltman. And it says that integrating over these 2 omega dimensions, this measure, d to the power of, let me get rid of that, of the term that appeared in our integral a minute ago. Now I'm using a q squared for the loop momentum and p for the external momenta. So that this integral becomes gamma 1 minus omega, where's the gamma function? 4 pi to the power of omega downstairs. Gamma 1, which is going to be 1 over m squared to the power of 1 minus omega is equal to this integral. And I'm skipping a lot of Laurent series here, right? I'm skipping references to complex analysis because you can kind of get around it. I mean, to do it properly, I'd have to bring in complex analysis. I just want to be able to get you guys to be able to carry out simple calculations and see where the renormalization comes in. So I'm going to have to clean the board, get your hands around that. You got your heads around that? We're evaluating this guy here, by the way. This is just 1 over p squared plus m squared. It's done already, isn't it? It is the propagator. This is a propagator, and a loop integral. I've gone through all this already. Once again, we're renormalizing a scalar field theory, lambda 5 to the 4th, and we're just doing it to order first order, because actually really what I'm going to do is just renormalize mass, okay? To show you how you can get a simple renormalization group equation for mass. I have a new board because I covered it with arrow holes. Where was I? So that was what I was doing. Now the rest of this is just playing around with small details, 1 over epsilons and 2 omegas and things like that. So we're going to say that our diagram, this one, we just say it's C1. C1 is 1 over p squared plus m squared squared. Now using the dimensional regularization formula, I'll plug in all the results. The previous formula. I wonder if I missed a step there. Yeah, I missed a step, so let me go back, let me backtrack a bit, let me turn that. I missed a page, a whole page. Now this is the last thing we got this before. That was the combinatoric factor. Combinatoric factor was something like that. Now when I rescale, change the lambda dash. And introduce dimensional regularization. I'm going to keep the external terms. That's what that is. I'll call this the new dash. Applying the 't Hooft formula. Hooft's formula going in now. And now this just has to be manipulated. We just have to manipulate out these guys, where omega equals 2 minus epsilon. I'm going to put in epsilons in place of omegas because I want to extract a pole, 1 over epsilon, because epsilon is going to go to 0 when omega goes to 2. 1 over 0, that gives the pole. All right, what next? So I'm just going to let C1 so we get our diagram equal to All I've done is I put in 2 minus epsilons in here for every omega. Gamma 1 is 1. It's going to get simpler. And I get down to a very simple result for this whole object here. This one. Okay? And on the next page I'll work it out. I'll change the formula. I'll bring some of these guys upstairs. So, that's our very neat little result. Now I've run out of space. I'm going to have to get you to copy this. You need to get down to this case here. Transcribe it, because I'm going to erase everything in a minute. It's going to get erased. You ready for it? Let you get your heads around that first. All I'm doing here is replacing omega with this guy, 2 minus epsilon, to extract the pole 1 over epsilon. Which is going to happen in a minute. And we're using the gamma function. So, what next? Okay, that's what he got. I'll write it down again, actually. I'm changing it a little bit. Epsilon. I just brought an m squared upstairs. That's all that happened there, right? Now, the gamma function, gamma n plus 1 is n factorial, so it's also called the factorial function. Gamma 1 is 1. Well, gamma half is pi. We don't need this just yet, but it's useful to know that. And I'm bringing an m squared over here, and the 2 epsilon is up here, so we have 2 epsilon mu and an m squared with it. Okay. Now, hang on. Yeah, I have to put an m squared up here. Okay, so what we say about gamma epsilon minus 1? Using a different formula, we can get to show that gamma epsilon minus 1 is minus 1 into 1 over epsilon plus psi 2 plus epsilon over 3 pi squared over 3 plus psi 2 squared plus, minus psi 2 dash. Now you don't need this because epsilon is going to 0, so I'm not even going to bother with this part here. We're going to concentrate on this. And psi 2 has a particular definition. Psi 1 is equal to gamma, by the way. Gamma is known as the Euler-Mascheroni constant. What next? Yeah, so we get a simple case now. I'm going to expand out this as an exponential in a minute. You guys don't need to know what this psi 2 is. It is a number. There's a minus here and a minus here, so I'm going to get rid of that. And I'm going to put in, okay. Exponential log x, natural log x equals x. I'm going to use that result. So I'm going to go exponential log this one equals it. Now C2 I absorbed, it's another constant I defined. C2. It's just the external momentum. Now there's a 2 epsilon here because I'm going to use that in the expansion. Now order epsilon, I'll stick it in there because that term is going to go to 0. Now e to the x we're just using the exponential expansion here, and the quantity expanded out is going to be 2 epsilon times this guy here. I'm almost there. I'm going to erase the board. I'm going to get your heads around that. Take a photograph of it. You can backtrack in YouTube. The thing about YouTube is you can stop and take a picture, take a snapshot, and look where we're going. I'm sorry if I have my back to the camera all the time. I'm trying to rush. I'm running out of time. I'm going to put the final result, expanding out this, multiplying this by this. I'm going to put it up here because 1 over epsilon, this one, they're going to cancel, and you're going to be left with one pole and the end result. So, for this class, the end result is coming up here. Once again, we're calculating this loop diagram. Now don't forget, this is the lambda dash all the time. Now that's where I have a factor of 2. I'm not sure why it's there. I may have made a mistake. I'm going to make one more final adjustment to this. I'll let you get your heads around that first. Got to move on. Now it's traditional to write this, not like that, but like minus this. For reasons that we'll see later. Okay? All right. Now the m squared over mu squared have dimensions of mass, so this is the dimensionless quantity. That's enough for now because I really had to rush through that and I run out of time.